This series focuses on data structures and algorithms content, and particularly in this recording I will talk the second part 2 of bubble sort algorithm, how to code a function implementing bubble sort algorithm. Let me start with this code to implement the bubble sort algorithm. First I need to have data. For the algorithm to work I need to have data, so let me create integer elements. Let me call this data equals to the values 18, 6, 3, 12, 9, 36, 21, 15. So how many? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 elements. Let me create a size variable. Const int size equals to 8 and use that variable here. So we have a data. We want to place these elements in ascending order. So let me have a function to display it, which receives the data for only display size, and it actually iterates in a loop less than size I plus plus, and it displays element separated by space, and after that I want to put new line character at the end. So I can display this data by calling this function, passing data and size. So let me make sure that this code at least works, and I will go ahead and talk how we can write the code. So we have a terminal here. This is the command for compilation and linking, and this is the command for execution. So we have these elements displayed: 18, 6, 3, 12, 9, 36, 21, 15. So it is okay. So we can start talking how I can implement bubble sort logic. So I want to put that logic in a function, and I can call that function. Let me call this bubble sort. I want to pass because if I want to sort, then I need to pass array and again the size information. So I should be able to call this function in this way. So the signature of this function should be because I didn't care what this function will return, so I put void as a return type and name of the function bubble sort, and the data I want to receive is here I cannot have a constant keyword because bubble sort actually does sorting changes in the array itself. It is a in place sorting. So let me remove constant. Now how it works is first we iterate the first we actually, for example, if I want to do sorting, let's say, and let me have a variable to do sorting, int temp, and I set temp equals to, let's say, data 1, and data 1, sorry, then let me call this, yeah, data 1 equals to zero, data 0 equals to temp. So this is a swapping process. So if I want to generalize, then I can create a variable, let's say int I, and initialize equals to 0. Let me call this j instead of I. So I can have j here, j plus 1, j plus 1, j. If I do like this and print this array after this, after the invocation of this function, and I want to see what happens. So let me go ahead and try to compile and link and execute. So you can see in the first we did swapping, so we are able to swap this 18.6. So in sorting, we want to make sure that the larger size element actually is placed after the smaller size element in all the possible pairs, not only in the first pair, right? So in this case, that condition is satisfied for the first pair, but for the second pair it is not satisfied. So we have to make sure that that happens for all elements. So what we can do is we can do iteration here. We can do this in an iteration. Let's say for j less than because largest index that you can access is size -1, because it actually starts from 0. So there are total size number of elements. So largest value this index can get is size -1. So it's going to be, but when we have index j, it will also access the one step, the next element j plus 1. So we can go up to size, not size but -1. So that j will go take a maximum value j will take will be size -2, j plus plus. If I do this thing here, then what happens is that it will do the swapping in all cases, right? So if I go ahead and try to compile it, so it actually did swap 18.6. So 18 went here. It did swap then 18 and 3. So 18 went after there. And let me just do this. Let me changes to the code, because I actually want to print this data at this point, right? So I want this function to be able to access this print function. So let me have a prototype of this function before. Here, and call this print function. And we can see what the exact steps that are actually taken when doing that operation. So we can see in the first case 18.6 were swapped. In the next stage this 18 and 3 were swapped, and this is the result. And the next stage this 18 and 12 were actually swapped. In the next stage 18 and 9 were swapped. In the next stage this 18 and 36 are swapped. So in this case we don't want to swap. After the result of swapping should be that the smaller element comes first and the larger element comes after. So this step we don't want. We want to skip this swapping step. And then after that this 36, we actually want to swap 36 and 21. So 36 goes in this position, and we want to swap this 36 with 15, so that at the end of this entire iteration the 36, the largest value, actually comes to the final position. So for that purpose we need to actually make sure that we check whether this first element is smaller than the second element, right? Only you do swapping if first element is not smaller than second element. So for that purpose what we do here is we actually have a if statement before swapping. If data j is less than j plus 1, in that case we do swapping, otherwise no. If it is not less than, that means not of less than, or if you want to be more specific, you can just do something like this. If it is greater than data, then you do swapping, otherwise just ignore it. Now with this we should I expect that that largest element will go to the last position. So let me see whether that actually happens or not. Compile and link and execute. Now you can see it was swapped at this point. This was just ignored, right? So swapped, and now it was less, so it was just ignored. This step was ignored. Then after that it was these two elements were swapped. So 36 went here, and they were swapped. 36 went at the last position. So at the end of that iteration, it actually went to the last position. That is what we want. Then once it goes to the last position, we want to lock it. We don't want to toss this anymore, right? So what we want to do is we want to actually restrict this upper bound, right? So in the next iteration, we want to run this again one more time. In the next iteration, we want to restrict the maximum value j can get, so that it doesn't reach the last element. So for that purpose, we want to have another loop, int I equals to 0, I less than, let's say, some value. Let me have size -1, I plus plus. Let me, for the sake of simplicity of explanation, let me have I equals to 1, right? In this case, in the previous case, if we in this case I can have I minus 1 minus 1. Let me use, just to, so for the sake of generalization, let me use I. So in this case, in the next iteration, once the first iteration data is output, then in the next iteration it will go up to index, let's say size is 8, 8 minus 1 7, 7 minus 1 6. So less than 6 equal to 5. So our iteration will move from 0 1 2 3 4 5. So j equals to 5 will access this both elements pairs. So the last element will be left, which was actually locked, right? So for that purpose, we have this I, and we want to continue that. In the next iteration, we actually display, let me just have this to be invoked. Let's say for int I equals to 0 and I less than 2, I plus plus. In this case, the first iteration would be, in the previous case we had if I was 0, then that would be exactly what happened in the previous case. So we didn't have this variable. That means essentially you can say that we are assuming I equals to 0, and first round of swappings actually completed, and the largest value 96 went to the last position. Then after that, in the next external iteration, I will go to 1, and it will actually not, it will make sure that this inner loop does not get access to the last element. So then it will only work on all the elements except the last element. So let us see whether it works or not. So let me go to the terminal, try to compile and link. So we have 18. The 36 was placed, this was the outcome at the end of the first iteration, and in the next iteration actually it went ahead and swapped 6 and 3. It swapped then 6 and 12. It swapped 6 and 3, and 6 went here, and 6 and 12 was swapped. 12 went here, 12 went here, and 12 and 9 were swapped. 12 went here, and no, 6 and 3 were swapped. 6 went here, and this this comparison was skipped because it is true. 6 is smaller than 12, so we didn't need to swap. Then after that, 12 and 9 were swapped. 12 went in this position, 9 went here, and after that this was no need to swap, and here there's need to swap. So no, there is no need to swap. In this case, no need to swap. In this case, no need to swap. Those steps were skipped, and there was a need to swap. 21 and 15. So 15 went here, 21 went here, and it didn't toss 36. There's no need to toss. Even if it was tried, it would not do anything, not swap. But we don't want to do that. Is not necessary. So now the second last element actually is placed in the second highest position here. So 36, this is 21 is the second largest number, and the 36 is the largest number, right? So these two elements are now swapped. So if I do make a little bit change to this I, maybe increase to 3, I will have 3 elements swapped. So you can see these 3 elements are swapped, and essentially all these elements are swapped, but this is not the case all the time. If these elements are not very friendly in terms of their ordering with respect to the increasing order, then they may not be in this order. So you need to follow all the steps. So first iteration to second, third, and you need to actually go up to in this case it is size minus 1, right? So that in the last stage, for example, if I is size minus 1, in that case this expression will be essentially size minus 1 minus size minus 1. So it will be equals to size minus 1 minus size plus 1. Right, so this size will cancel the size, and 1 this result will be 0, so it will go up to 0. So when it is 0, less than 0, so it will not iterate. At this point there will be only one element under consideration, so you don't want to consider that element only one element, because you need to pair just to compare, to swap. Therefore it will automatically exit, and then it will exit external loop as well. So this will actually end the entire sorting process. Final. So this is at the end of the sorting process. We have everything sorted in this form, and what else? And in addition to this, we have some ways of making this algorithm efficient. For example, if you want to skip this swapping, this all the iteration after everything is ordered. For example, if I have data like this, where all the elements are actually in increasing order, already increasing order. Let's say 3, 6, 12, 9, 12, 18, 15, 21, and 36. If you have this kind of thing, then we don't need to go through all the iteration. That would be waste of time. So in that case, you can do something to actually minimize those iterations. Let me see. Number of elements is 1 2 3 4 5 6 7 8, right? So in this case, if you want to make it efficient, then you can create a boolean variable, maybe is sorted or something. So initially you can assume that true, and here at this point you can set it to I don't think you need to initialize here at this point. So you have a sorted is true, and if in any case, if this let me comment this out. So if swapping happens, then is false. I think we need to initialize because we want to make sure that it enters the loop. So let me have equals to false, and you can allow it to enter when it's false, is not, is so whenever this variable carries the false value, it will be it will continue. If this variable carries true value, this condition will be false, entire condition will be false, and it will immediately exit the loop and it will not continue. So in this case, we assume that it is sorted, and if there is at least one swapping, and it will actually reverse this value, and this iteration will continue. But if this in the inner iteration there is no single instance of the swapping of the values, then this variable will carry true. That means there is nothing to swap. All the adjacent elements are actually in the sorted order. So this will true, and true will automatically make this expression false, and that will actually render this expression false, and it will exit. So it will not continue with the next round of this iteration. So that will actually help to minimize these things. For example, if I actually display this data to see how many times it gets iterated, I may print data and size here. Maybe display something, some text, just to as a marker, and we'll see how many times this loop, external loop, will be iterated for this already sorted data. Okay, so let us see. So there is only one time iterate because it is already sorted. It ran one time, and the next time the is sorted variable was actually true, so it didn't continue with that iteration. So we minimize the amount of computation here. But in case if we have a different data, for example, everything is not sorted, entire data is sorted in, let's say descending order, at equals to, let's say first element is, let's say 36, second 21, third 18, and fourth 12, 9, 6, and 3. Let me count it: 1 2 3 4 5 6. Anything missing? 36, 21, 18, 15 is missing, 12, 9, right? So let me run the same algorithm with this data. We can see this iteration continuing because it has to reverse all the elements. It continued for 1 2 3 4 5 6 7. Total, it continued, iterated for maximum possible iterations here in this case. So this is all I have to talk about the bubble sort and coding in bubble sort. In the next recording, I will talk about analysis of bubble sort algorithm. Thank you for watching this recording.